Welcome to Net Zero Energy Architecture. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. The net zero energy practice is integral to achieving sustainability in the built environment. We'll explore how buildings use sustainable design strategies and balance energy consumption with renewable energy production. By the end of this session, you will have a good understanding of how net zero energy buildings are realized. This slide lays out the overall framework for achieving net zero energy in building design. In net zero energy buildings, the net means that the building's energy use is balanced by the renewable energy production. If renewable energy production is more than the building's energy use, it is referred to as a net positive energy building. The bubble diagram shows an approach to reaching zero energy buildings. Now let's discuss the net zero energy framework with three interconnected elements: bioclimatic design, energy efficient building service systems, and renewable energy integrations. First, bioclimatic design is a fundamental step toward net zero energy strategies and should be integrated from the beginning. It leverages climate and site resources to create a healthy, energy efficient building. Bioclimatic strategies use natural ventilation, natural cooling, daylighting, and solar heating, all without the need for active service systems. In this way, the energy demand for active systems is minimal, which is the next step of achieving net zero energy buildings. Next, high-performance MEP and LED lighting systems should be incorporated to further reduce energy use. Incorporate primary HVAC equipment and terminal units according to project needs, considering cost, energy efficiency, spatial implications, and other performance measures. Finally, bioclimatic buildings operated by energy-efficient systems still demand power consumption. On-site renewable energy production, such as solar panels or even creative solutions like wind or biogas, enables a building to become net zero or even energy positive to supply energy use. Additional videos are available for each strategy as shown next to the bubble. They are Bioclimatic Design, Sustainable MEP Integration, and BIPV and Solar Facades, in addition to net zero architecture in this video. The net zero energy strategies can also be organized under two main approaches: reduce and regenerate. Think of the zero energy design framework as a balanced scale as shown on the right. On one side, we have reduce, focusing on minimizing resource consumption and energy demand. Bioclimatic design is a way to reduce energy demand from the outset, while energy-efficient service systems will further minimize operational energy. On the other side, we have regenerate, emphasizing the creation and replenishment of resources such as solar, winds, and others. When these two sides are in balance, or when the regenerate side surpasses the reduce, the net zero energy design achieves its goal. In other words, it emphasizes that both reducing consumption and generating renewable energy are integral to the net zero strategy. Slides 8, 9, and 10 will quickly go over an overview of each net zero energy strategy. Bioclimatic design effectively leverages local climate and site conditions and is the foundation of net zero energy buildings. Climate factors such as humidity, temperature, radiation, and air movement affect building design. As a result, buildings respond in their form, orientation, facade design, natural ventilation, daylighting, and space organization. For example, window designs change with orientations for shading on the west to block harsh afternoon sun, or taking advantage of north light for consistent daylight without heat. These strategies form the reduce side of the net zero approach and should be considered first. This slide shifts focus on the technological side of reducing energy consumption. The use of energy-efficient MEP systems and LED lighting achieves low energy consumption while providing comfortable environments for users. Building Management System, BMS, is a computerized central system that monitors and optimizes entire building operations. This high-performance service system is integral to the reduce framework, complementing bioclimatic design to further minimize energy demand and enhance occupants' health and well-being. Sustainable MEP integration video is available. The final strategy of net zero energy design is the integration of renewable energy systems. The ability to generate clean energy effectively allows the building to offset the remaining demand after bioclimatic design and energy efficient systems integration. Examples shown here demonstrate a wide range of solar applications at the infrastructure level, such as photovoltaics, solar desalination, solar farm, and solar canal. In urban settings, examples include solar-powered street lamps, solar benches, solar parking decks, and solar acoustic barriers. In building integrations, examples include facade applications such as Blauhaus, Novartis Pavilion, and FKI, and roof applications such as Apple HQ. These examples convey that integration of renewable energy strategies is versatile. By designing from the start with renewables in mind, whether it's BIPV on a curtain wall or a solar panel on a parking structure adjacent to buildings, we ensure that clean energy generation is harmoniously built into the project, paving the way for net zero energy operation. BIPV design and engineering, as well as solar facade videos, are available. Using the figure here, let's include a progression of EUI reductions as each net zero energy strategy takes place. In order to verify that we're on track toward the net zero energy goal, we rely on energy metrics. One of the most important metrics is energy use intensity, EUI. EUI is the total annual energy consumption divided by the gross floor area, represented by kilo BTU per square foot per year, or kilowatt hour per square meter per year. It is a similar concept to miles per gallon. Higher EUI means the building energy use is high. Lower EUI means that the building energy use is low and using energy more efficiently. The baseline EUI shown in the green bar comes from an actual survey from the Commercial Buildings Energy Consumption Survey, CBX. For an office building, a rough baseline could be around 68 kilo BTU per square foot per year, which is the national average for existing buildings. Using our net zero strategy, we then calculate the improved EUI after applying all our energy saving measures. Once bioclimatic design is complete, let's call the resulting EUI as EUI X-Tex. Use bioclimatic tactics such as building orientation, building shape, natural ventilation, natural shading, thermal insulation, daylighting, and balanced percent window-to-wall ratio, percent WWR. Software simulations are available to accurately quantify EUI X-Tex. For the sake of presentation, let's assume EUI X-Tex 40. We then explore pushing the performance further. Let's say your building incorporates state-of-the-art, energy-efficient systems such as smart LED, geothermal heat pump, VRF, and DOAS. Assume 50% savings from these energy-efficient systems. Once efficient systems are implemented, the resulting EUI will be referred to as EUI-YY. Because specialized expertise is required to simulate such systems' energy savings, let's use EUI-YY 20, a 50% reduction from EUI X-Tex 40. By cutting EUI X-Tex in half, we've dramatically reduced energy demand to EUI-Y 20 kilo BTU per square foot. Next, EUI-ZZ is an even more ambitious case achieved by adding on-site renewable generation that drives the net energy use down closer to zero. At the far right, the blue bar from BIPV is negative, representing the offset of EUI-YY and the ultimate net zero goal. In the next slide, we will cover how to calculate BIPV areas required to offset EUI-YY 20. In summary, this chart visually highlights the journey from a standard EUI 68 baseline down to net zero. Each step from our initial CBEX data EUI 68 to bioclimatic design at EUI 40 to efficient system integration at EUI 20 and finally to EUI 0 after renewable energy integration. This process illustrates how much improvement is needed and how our strategies contribute to closing the gap toward net zero performance. This analytical approach gives us confidence that our design will perform as a net zero energy building in operation. This slide explores a hypothetical office building to show how solar potential translates into reality. From the solar map, Charlotte's solar energy potential is roughly 4.5 kilowatt-hour per square meter per day of sunlight on average. If we use a solar system with about 20% cell efficiency, each square meter of panel could generate about 0.9 kilowatt-hour per day, equivalent to roughly 330 kilowatt-hour per square meter annually. That is about 110 kilo BTU per square foot per year of energy from the sun. This is the theoretical solar supply we can tap into on our building facades or rooftops to offset the previous EUI YY20. Now let's calculate required BIPV area. Imagine a 50,000 square foot office with EUI YY 20 kilo BTU per square foot. That means the building needs about 1 million kilo BTU annually from EUI YY, 20 kilo BTU per square foot times 50,000 square foot. Given Charlotte's BIPV potential of 110 kilo BTU per square foot per year, we will need on the order of 9,500 square feet of BIPV area from 1 million kilo BTU divided by 110 kilo BTU per square foot. This means covering the spandrel curtain walls and roof area as illustrated in the figure on the right. The takeaway is that to achieve net zero energy, demand and generation must be in balance. Even a high-performance 50,000 square foot office would have to allocate roughly 10,000 square foot facade, including other accessories to meet its yearly energy needs. Designing for net zero goals has broader implications on the site design, buildings form, and space planning. We are not only aiming for net zero energy, but also net zero carbon, water, and waste, and each of these has architectural implications. Our first architectural precedent is the Germantown Friends School Science Center, LEED Gold Certified Science Building in Philadelphia, completed in 2009. 1. Reduced through bioclimatic design. The building geometry and orientations are taking advantages of sunlight and prevailing winds for shading, winter solar heating, and natural ventilation. The building also provides access to ample daylighting and view out. 2. Reduced through high-efficient systems. Energy-efficient systems for the building include geothermal ground-coupled heat pumps for heating and cooling, along with LED lighting. As a result, the building reduces modeled energy use intensity to around 43 kilo BTU per square foot per year, less than half of a typical science building. 3. Regenerates solar power to offset the energy demand. Solar panels on the roof supply the energy demand. However, because of small solar roof areas, they could not power the entire building, but a portion. Additional energy efficiency and renewable strategies are so important for approaching net zero in such contexts. Continuing the same project, stormwater management is integrated into the building and site. Water-efficient fixtures and efficient plumbing practices minimize water usage. The building incorporates green roofs, cisterns, and a courtyard rain garden. These building and site features greatly help both runoff mitigation and water collection. The rainwater runoff from the roof goes to 2 large tanks called cisterns. These tanks store rainwater, which are used to flush toilets. This building and site serve as an educational testbed to teach environmental challenges and sustainable solutions. Next precedent is the Echo Building at TU Delft, completed around 2020. This building is celebrated as the first truly net zero building on the Delft campus. 1. Reduced through bioclimatic design, high-performance facades, operable aperture, and optimized daylight reduce the demand for heating, cooling, ventilation, and artificial lighting. The atrium at the center serves as a buffer to adjacent climatized spaces. 2. Reduced through energy-efficient systems. The building also uses an underground thermal storage system to efficiently regulate indoor climate, further reducing reliance on active mechanical systems. Space is conditioned through direct air supply in the occupied zone for most efficient use and highest level of comfort. Dynamic lighting and sunscreens combined with convectors help prevent overheating and cold downdraft. 3. regenerate solar power to offset the energy demand. 490 photovoltaic panels spanning about 750 square meters of roof area harvest the sun's energy. These solar panels generate roughly 150,000 kilowatt hours per year, which is enough to cover 100% of annual energy consumption. Solar panels are well integrated with the roof, essentially turning the building's top surface into a power plant without spoiling the aesthetics. This precedent demonstrates that net zero is achievable with bioclimatic buildings coupled with high-efficient systems and sufficient solar panel areas. Our next precedent is the Daniels Building at the University of Toronto, completed in 2018. This project blends a restored historical Gothic structure with a contemporary new addition. This project wasn't designed to be net zero, but it embodies many sustainable design principles and provides a realistic benchmark for a large institutional building performance. 1. Reduced through bioclimatic design strategies. The addition reused the massive thermal mass of the historic stone structure and employed modern environmental strategies. Limiting large glass exposures on the east and west facades reduce heat gain, taking advantage of orientation. They upgraded insulation and systems throughout. The skylight brings in ample daylight. 2. Reduced through energy-efficient systems. Efficient HVAC strategies include hydronic radiant heating and cooling embedded in the concrete slabs of floors and ceilings. These radiant surfaces and efficient air distribution minimize the fan power and ductwork needed for air conditioning while maintaining a high level of indoor comfort. Geothermal wells on-site coupled with DOAS in mechanical rooms in the basement operates building with less energy demand. After bioclimatic design and efficient systems are complete, the building operates at a net EUI 62 kilo BTU per square foot per year, which is about 40% lower energy use than a typical comparable building. 3. Regenerate solar power to offset the energy demand. For space and surface implications, even with a decent EUI 62, it appears that a large building consumes a huge total amount of energy simply due to its scale. Based on the previous quick calculation, if Daniels' energy use was to be offset by a solar system, it would need tens of thousands of square feet of solar panels. In other words, the available surface on the building is far too small relative to its huge energy demand. The Wave Sports Hall at Nanyang Technological University in Singapore, opened 2017, exemplifies a net zero energy performance through integrated structural and environmental design. Its most distinguishing attribute is the expansive curving timber roof made of glulam arches, which is 72 meters in length and creating column-free arena. 1. Reduced through bioclimatic design strategies. This all-timber roof and frame provide natural thermal insulation about 5 times more effective than concrete, drastically reducing solar heat gain and the need for cooling. Instead of conventional air conditioning, the Wave relies on natural ventilation augmented by innovative passive cooling technologies. Each external wall is built as a double-skin facade with an air gap for insulation and contains special chilled water coils that pre-cool incoming air. 2. Reduced through energy-efficient systems. The induction cooling system cools breezes as they flow through the hall, while warmer air rises and escapes through convection vents. Chilled water coils, coupled with heat pump equipment, reduce energy consumption compared with air-based cooling system. Smart LED lighting further reduces energy demand. 3. Regenerate solar power to offset the energy demand. Solar panels are installed to provide electricity needs, achieving net zero energy performance. Takeaways include 1. Dual strategy, reduce and regenerate. First, minimize energy demand through design and efficiency, then supply the remaining needs with on-site renewable energy generation. 2. Integrated design elements. Lower demand, multiple design features work together to drastically cut energy use. 3. Net zero goals, shape design, surfaces and spaces Pursuing net zero in energy, carbon, water, and waste means the building itself integrates sustainable systems. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Together, we can advance towards a sustainable and net zero future.